Tonight, Carbon and Earth's Atmosphere by Dr. Leslie Ott. Enjoy.
So hi, my name is Leslie Ott and I'm a climate scientist at NASA's Goddard Space Flight Center. Most of my work focuses on trying to understand the sources and sinks of greenhouse gases in our atmosphere. So today I want to show you some of the ways that NASA tracks carbon dioxide, the main driver of climate change, as it moves throughout the Earth system. Next slide, please. So let's start by looking at a movie that shows you the view that scientists have had for a number of years of carbon dioxide. This is made by stitching together a number of air samples that are made at remote stations around the world. So on the left, you're going to see the north to south gradient of carbon dioxide, and on the right, you're seeing the time record of how global concentrations have changed over the past 40 years. So even from this relatively small handful of stations that you can see on that inset, we knew some really important things. So first, we could see that there was seasonal variability in the carbon dioxide record. You can see this is most pronounced in the northern hemisphere, and that's because we have a larger landmass in the northern hemisphere. We've got more plants on the land that draw carbon dioxide out of the atmosphere every spring and summer, and then re-release some of that carbon dioxide in the winter. But the second thing you notice, sadly, is that carbon dioxide concentrations continue to march steadily upwards year after year. And even though scientists have known both of these things for a number of years, we haven't always had the details that we need to understand the human and natural factors that control carbon dioxide and to be able to predict how they could change in the future. Next slide, please. But luckily it's NASA, and we have lots of satellites to help. NASA operates a fleet of about 20 Earth-observing satellites, and we collaborate with other US agencies and international partners on many, many more. So satellites are unique in giving us this really beautiful God's eye view that allows us to see beyond our own neighborhoods, our own homes, to see the whole planet, and to measure the world at different wavelengths of radiation beyond what our own eyes can see, so that we can get different perspectives on the many factors that influence Earth's weather and climate. So in this animation, which kind of looks like a beach ball, we're looking at some of the many different types of observations that our satellites make. So in the atmosphere, for example, satellites help us see things like clouds and tiny particles of pollution that can affect human health. On land, satellites can actually allow us to peek beneath the surface and see soil moisture, which helps us understand risks to agriculture. And satellites actually help us track temperatures across the world every single day. So these data have really shaped the way that we understand and predict the health of our planet, and they also allow us to track all of the major components of the carbon cycle. Next slide, please. So first, let's start by looking more at the human dimension of carbon. This is a view of nighttime lights from NOAA's Suomi NPP satellite. The idea that we could get a sense of human activity from space actually dates back to some of the early photos that astronauts have taken from the space station. You've probably seen some of these. And in the 2000s, scientists started to put together this first of its kind data set by working with images that were actually collected by Defense Department satellites. And they composited all these different clear sky images that they could get these pictures of what typical patterns of nighttime light activity and energy usage look like. So the view from newer satellites like Suomi NPP has allowed us to get even more detail in our cities and suburbs, and it helps us track how energy usage is changing over time. So we can look at long-term trends. For example, we've seen dramatic changes over much of India, but we can also see short-term variations like those related to COVID-19 restrictions, recovery in areas like Puerto Rico that have been hit by major hurricanes, and even changes in fishing activity from boats at the sea. That's how sensitive these data are. But they're also a lot more than a pretty or interesting picture. We take these data, we combine them with national level information about carbon emissions to create very high resolution maps of human emissions around the globe. Next slide, please. So as we saw from that first animation of carbon dioxide concentration, humans aren't the only influence on carbon dioxide, right? This animation is showing us the color of our land and oceans, and it comes from two instruments we call MODIS on NASA's own Aqua and Terra satellites. And so on land, the colors that you're seeing are showing you how green or brown the land surface appears. We've actually tracked the greenness of vegetation since the 1970s with satellites. And as the globe spins, you can see some of those seasonal variations that we first saw in that simple line plot of carbon dioxide. But in this global view from the satellites, we can actually see where and when the plants come to life all over the world. So scientists use these data to study how vegetation responds to climate change. For example, we're seeing lots of changes in greenness in high latitude regions where there's warming faster than anywhere else on the planet. But people all over the world, not just scientists, use these data to track things like the impact of droughts, to fine tune and maximize agricultural yields, and to keep tabs on the health of remote forests in their regions. So the same satellites that actually help us track life on land are helping us understand our oceans too. Here, when you see the oceans, the warmer colors are showing us higher concentrations of chlorophyll. That means a greater density of tiny plants called phytoplankton. And it turns out this capability to see both the land and the oceans is really important because in the oceans, phytoplankton and seawater both absorb carbon dioxide. So every year, our world's oceans and the vegetation on land do us this enormous favor. They absorb about half of human emissions of carbon dioxide from places like power plants, things like transportation. So without this natural assist, carbon would be building up in our atmosphere about twice as fast, and the planet would be much warmer than it is today. So overall, this is great. This is very helpful. But the big problem for scientists is that we don't know how long this assistance is going to continue and how it might change in the future. So this is one of the biggest uncertainties in climate projections over the next century. And it directly affects the goals that countries around the world are setting to reduce their emissions in order to manage temperature increases. So continuing to monitor the health of our plants and our oceans remains a really high priority for both researchers and policymakers. Next slide, please. So the views that we've just been focusing on have shown us carbon at the Earth's surface. And I want to start there because that's where the science has been for several decades. It's really the foundation of our understanding of the science of carbon dioxide. But only recently have we been making high quality, high resolution observations of atmospheric carbon dioxide from space. So NASA's been making observations from its orbiting carbon observatory, or for short I'm going to call it OCO, since 2014, and our colleagues from JAXA in Japan have a record that goes back a little longer to 2009. So it turns out that even though carbon dioxide is incredibly important, it's also really, really hard to measure from space. That's because there's so much carbon in the atmosphere that our satellites have to be incredibly sensitive to very small changes. And it took us a long time to be able to make measurements that were actually good enough to be able to use for these purposes. So both the Japanese and American satellites use information in reflected sunlight to estimate the total number of carbon dioxide molecules from the surface of the Earth all the way up to the top of the Earth's atmosphere. So this animation is showing data collected by OCO, and the warmer colors are showing you places where there's more carbon dioxide, cooler colors show you where there's a little bit less carbon dioxide. One thing that you've probably noticed from this movie is that it looks a little different than the other ones. Instead of big wide swaths like we saw in those land and ocean pictures, this satellite is seeing the world in very thin 10-kilometer stripes so that it can actually peek between clouds and collect very accurate data. So even the OCO brings us many more observations than we've ever had, about 1 million per day, we still have these very, very important gaps in our maps between the ground tracks or in areas where it's dark or cloudy and the satellite can't see very well. Next slide, please. But luckily, when we don't have direct observations from OCO, we still have loads of other observations about the atmosphere, and we already use these data day in and day out to produce weather forecasts. So this is a diagram of all of the weather data collected in a 6-hour period by a combination of satellites, ground stations, and aircraft. And the colors are just representing different types of observations. So I particularly like the little yellow ones, which are showing you the information that we get from airplanes. So to predict the weather, what we do as meteorologists is we take complex numerical models, we stitch together all of these different kinds of data sets, and then we advance them into the future to see what the weather's going to look like 12, 24, 48 hours in the future. But these models and data sets do a lot more than predict the weather. They can help us tie together all of the data sets that we've seen on carbon dioxide sources and sinks. They can actually help us fill the gaps in OCO to create the world's most complete picture of carbon dioxide in the atmosphere. Next slide, please. So it's been a long road to get here. It took us dozens of satellites, a few supercomputers, and literally millions of lines of computer code. But we can now track carbon dioxide across the world and watch it move through the atmosphere. So in this animation, you're going to see it actually tilt down a little bit, and you're going to get a glimpse of the world of carbon dioxide in 3 dimensions. So this is an area where our computer models actually help provide additional information that satellites OCO, like OCO, can't directly observe. So here we're seeing more information on the vertical distribution of carbon dioxide. And that's really important for connecting that first surface-based view that we saw from this new space-based one, which are each giving us different but complementary pieces of information. With this information, we can do a better job of validating satellite data, comparing against things like aircraft observations, so that everybody can have confidence in the types of carbon dioxide measurements that NASA makes. It also shows us how global and truly interconnected the carbon pollution problem is when you look at this, right? And that's the whole point of COP. This is a big problem and no one can fix this alone. So as this one runs through, I also want you to note how the colors are changing over the course of a year. So when we started in the summer of 2020, we actually zero out the color at about 400 parts per million CO2. And when we end a year later, you're going to see this warm belt of colors, and that reflects the change in carbon dioxide over the past year. That's the positive balance from human emissions that stays in the atmosphere after that uptake from the land and oceans. Next slide, please. So over the past year, this view of carbon dioxide, this integrated three-dimensional picture, is the one we've reached for to understand how the COVID-19 pandemic was affecting our environment. So unlike some shorter-lived pollutants that come primarily from cars, carbon dioxide effects were more subtle during COVID. Independent estimates suggested decreases in human emissions during 2020 were between 7 and 10%. The combination of data from OCO and from other carbon satellites and these models helped us provide an independent check on some of those estimates, which were coming from economic data, and we could do that in something close to real time. So this animation shows you the change in column integrated carbon dioxide concentration due to the changes in sources and sinks in 2020. So the warm colors show you where we had more carbon, and the cooler colors show you areas where we had less carbon in 2020 compared to other years. So when we start 2020, you'll see the patterns are associated with natural variability, things like emissions from those Australian bushfires or changes in rainfall patterns over India and Africa that made for an especially good growing season. But as we transition into March and April, we see the impact of the lockdowns around the world takes over, and this small decrease in carbon dioxide becomes widespread, which is this sort of blue color that takes over. And by the end of the year, as life starts to get back to normal, we can see a return to more typical carbon dioxide concentrations where it looks pretty washed out. So it's important to know that climate change didn't stop during COVID. Carbon dioxide continued to build up in our atmosphere, just at a slightly lower rate than we would have expected without the pandemic. Well, what COVID-19 also showed us was the maturity of these carbon monitoring systems that we've spent literally decades of our lives building. So we're continuing to use this data set that I'm showing you right now to track changes in carbon dioxide as they happen and to translate those changes into radiative forcing and temperature. And we're doing that so that we can understand how all this carbon affects our climate. Next slide, please. So we're coming to the end of this presentation. I want to leave you with a glimpse of what we have coming in the future. So right now we're working on a satellite called Geocarb, and that's going to be the world's first geostationary greenhouse gas mission. So in this animation, we start by looking at the way that OCO observes carbon dioxide today from low Earth orbit. It's about 700 miles above the Earth's surface. And as we mentioned before, it's in these thin little 10-kilometer wide stripes. So Geocarb, when it launches in a few years, will travel way higher, about 36,000 kilometers into the air, so that it can rotate with the Earth and stare at the Americas to give us the information we need. So with Geocarb, we'll be able to scan most of North, Central, and South America once a day for a really huge increase in the density of data in those regions. That's going to help us study things like emissions from power plants, fires, and to help us monitor the exchange of carbon in really key ecosystems like the Amazon. We'll also be measuring methane from Geocarb, the second most important greenhouse gas emitted by humans. That's going to help us give an even more complete understanding of climate change to policymakers and help us to connect the science that we're doing with all of the good work that's going on at places like COP to help us protect the future of the planet. So thanks a lot for joining us today. We hope you'll be back to see some more work at the US Pavilion. Take care.